Hello, welcome to presentation of LowLAG. I am Yunus Emre and we present LowLAG with my supervisor İsmail. I will talk about a low latency hardware accelerator of a sound effect, which is a system-on-chip design. Today's world has many entertainment industries and these are used sound effects. Music is one of them and the sound effects are very important in there. Artists use sound effects for their voice or instruments and they always want to hear affected sound in real time. So, what is real time? If affected sound is coming back to the ear in 5 milliseconds, it is real time for human. Otherwise, human brain notices the latency. CPU-based solutions have limited processing power. Because of that, we need specialized hardware to reach beyond. So, how latency occurs on CPU-based solutions? Microphones sense the audio sample by sample. CPU cannot reach speed of samples while they are processing if they are sent sample by sample. CPU makes calculations and needs so many things to realize your design. It may cost too much instructions, which means that will be cost of latency as well. This also corrects the audio and this is really bad to hear. To avoid correct audio, buffers can be used. It reduces the load of the CPU, but the delay when audio samples going to buffer creates more latency. This latency prevents the obtained processed audio in real time for complex calculations. So, how we can obtain low latency values with application-specific hardware applications. This application-specific hardware is designed to obtain as minimum as possible latency values. It provides make processing sample by sample through high-speed registers. We don't have rich memory or other peripherals. All processing is on a chip that is brought reduced latency values. Which solution is better for these applications? Software or hardware? Software solutions give more functionality, but it causes more latency. And hardware solutions gives more efficiency and speed, but causes lose flexibility. We can choose both. System-on-chip design provides of use advantages of both hardware and software together. We have hardware-software co-design methodology. So, what is LowLAG? LowLAG is a system-on-chip design for a sound effect. It uses hardware and software together. LowLAG takes your audio and processes it with low latency compared to CPU-based solutions. We already said that advantages of software and hardware together. When we use hardware and software together, we take advantages of both and get rid of disadvantages. This solution was made on FPGA-based system, which name is Z-board. It also has an ARM processor. Thanks to the co-design methodology, we take advantages of speed of the hardware and functionality of the software. For the best latency value, it is necessary to design an application-specific programmable hardware. In order to obtain the best latency, an application-specific hardware is designed on an FPGA chip. This is a pure solution for processing the audio and the computations are made on high-speed registers in order to reduce latency. To do that what we talked, we have to create a custom IP, which is the application-specific part of the hardware in our design. When we create our custom IP, we have better execution times and high-speed registers. With the AXI4 interface, we can communicate with other IPs and processing system as well. To create our custom IP, first we designed a basic sound effect on Simulink. This design was converted to custom IP via HDR coder, which provided by MATLAB. This method saves a lot of time. The designed sound effect is converted to the IP core via HDR coder. It uses Xilinx synthesis tools to create VHDR code. In this design, we used Z-board provided by Xilinx. FPGA and ARM processor are worked together. The chip runs at 100 MHz. Lower frequencies causes loss of quality. Software runs on ARM processor and controls the hardware. You can communicate through the UART connection. So, how LowLAG is implemented? First, look at the basic working principle. Z-board has four main parts for this methodology. These are audio codec, custom IP, processing system, and AXI interconnect. Assume that an audio sample is coming from microphone. Audio codec takes the audio and transmits to the custom IP over the AXI interconnect. Processed audio comes back to the audio IP and then user can listen it. When you want to change a preset of the sound effect, processing system transmits that custom IP over the AXI interconnect. Let's look at the system overview. Z-board is the main part. We have programmable logic and processing system on it. Audio codec and sound effect IP blocks are added on the hardware design. And we have microphone and headphone. Microphone takes the audio and transmits to the audio codec. It sends the audio to the sound effect IP block and takes back to that. Finally, the affected audio can be listened on the headphone. Processing system can control preset of the sound effect. When we summarize the implementation, we need to create sound effect model on Simulink, convert that model to custom IP core, bring all IPs together on hardware design and composing the software according to hardware. The created sound effect can be shown on the figure. It is very simple effect for the demonstration. It mixes clean and distorted audio. Created model is converted IP core via HDI coder. All configurations for the board was made in there. We designed an IP core for our sound effect on LowLAG. As we said before, we designed the sound effect on Simulink and converted the VHDI code via HDI coder. Even if we didn't create our code via HDI coder, it would take so many time to complete. If you want to create a sound effect on a chip, you can focus your design more. Also, this code is reliable and already tested. IP core was packaged on Vivado and the custom IP is shown like that figure. AXI interface is also shown in the figure. When we expand the AXI interface bus, we can see a lot of signals there. These signals are controlled 5-channel that can read data or address and also write data, address or response. This interface provided making communication between IPs or processing system. You can see the whole FPGA design of the LowLAG system. This design consists of 2 parts. The first part is processing system, which means our software part. The second part is programmable logic, which is the hardware part. 2 parts are communicated through AXI interconnect. Hardware contains LED controller, distortion sound effect, GPIO ports such as buttons, and audio codec IP. The most important IP is the distortion IP, which is our designed application-specific hardware part. We have been used Vivado 2015.1. Also, we made use of Zinc book tutorials. The software was made on SDK. Designed hardware introduced that software thanks to the Vivado. This software imports and exports the audio, determines the IP connections and registers, and also communication processes over UART. Hardware and software are co-designed. ARM processor communicates with IP cores by defined expressions. Hardware specifications are defined on software with drivers and board support package. We can use any part of hardware by defining, like code is shown. For example, defined register address for sound effect is defined in distortion IP driver. 3 different experiments were done for obtain the latency values on CPU-based solutions and LowLAG solution on Z-board. The Simulink experiments made on 2 different drivers. You can see the test specifications on there. 2 different experiments have been done on Simulink, which were used direct sound and SO for all drivers. The best result is 2.8 milliseconds, which has been made on SO for all driver. The Z-board experiment has been done also. Results are calculated over TTC timer. The latency value for LowLAG system is 1011 nanoseconds. There is no buffer or sample frame for this experiment because every sample is processed on register one by one. When we compare the results, we have 2 solutions as we mentioned. Simulink solution with SO for all driver has 2.8 milliseconds latency and LowLAG has 1011 nanoseconds latency, which is almost 1 microsecond. Latency of LowLAG 2769 times better than Simulink solution. This result proves that LowLAG reduces the latency considerably without lose functionality. Our LowLAG design shows that hardware-software design provides big advantages. Design on Simulink saves time, and this application can be used on many different industries. When we summarize it, latency is too important for audio applications. LowLAG SoC solution comes up with low latency values and lower complexity, thanks to the customized hardware and high-level description we have MATLAB HDL coder. Real-time low-lag SoC are evaluated on the latest FPGA devices. Distortion effect is a basic effect to show low-lag solution. More complicated sound effects can be designed and implemented on low-lag in the future. Thanks for listening.